the approach that we take is we make sure that even with these higher motion ratio suspensions, we make sure that we still are setting them up so that we have at least 50 mil of drip travel. And that's, again, partially about what the tire's doing on the track surface and partially about what's happening with the damper and allowing the damper to have, like, allowing the piston to be able to actually travel within the damper before it tops out.
Green flag.
Welcome to the Blind Apex Podcast, where amateur club racers tune in to get faster.
This episode is brought to you by DeechWorks Fuel Systems. Use Apex 10 at checkout to save 10% on fueling your passion. Speaking of discounts, use Blind Apex 2025, all one word, to save 20% off a monthly or annual Race Setup Pro plan. And if you want to support the podcast directly, go to buymeacoffee.com/the Blind Apex Podcast. On this episode, I want to go over suspension frequencies and catch up with my guest. I've seen a lot of this stuff on the internet, lots of reels, and for some reason, when reels start happening, people start DMing me like the idiot with the mic is the one that has the answers. I don't. I had to go seek help. And I decided to seek help from a guy that's determined the suspension frequencies on my car, which I sort of understand, but I actually don't understand that much. So joining me from about 16 hours in the future, and someone who's in a polar opposite season, making parts for Hondas, except for old Accords. I didn't see the Accords on there, not the old ones anyway. But he even makes NA and B Miata parts. Grant from Hone Developments. Welcome back to the podcast, sir.
Thank you very much. Good to be talking with you again.
Yeah, it's been, I don't know, we were talking before we hit record. You said 16-ish months?
It's been 16 months, and we've been really busy. I've been full-time working in Hone, growing the business. We've been doing a lot of like mini projects on our own cars and on our projects, and also releasing new products. We now, as of my last count, we have 170 products across 16 different types of Honda. And you're right, not on the some of the older, less used for motorsport Accords we don't yet or don't do anything for, and we do for the NA and NB Miatas. And we also, in more recent times, have brought out some universal products, so not so much chassis specific. Since we last spoke, I know you've been talking about and looking into introducing or setting up your car with an AM data logger or data logging system, possibly a dash, possibly some other arrangement. We've been running with the AM Solar DL, which I had talked to you about, and that works well for us because we have multiple cars. So being able to move the system between cars adds a lot of value. And one challenge that I found was that trying to implement a brake pressure sensor was actually not very straightforward. Some of the cars where they have a completely custom brake system, you may have already strayed away from the standard invert flare or bubble flare brake line setup. Putting the brake pressure sensors in with, like, say, a banjo bolt or some other mounting arrangement, that's one thing. But on the cars that are nearly stock, where you don't really want to disrupt much else about the brake system, you just want to put a brake pressure sensor in, I couldn't find any easy way of doing that. So I came up with a little adapter that allows you to it's quite short, and it allows you to just undo a brake line, say from the master cylinder or from the input into your ABS unit, pull the brake line back a little bit, put this adapter in, and then put the AIM brake pressure sensor directly into the adapter. And then you can then electronically plug that into your data logger, and straight away you've got brake pressure sensor on the car. And what's really useful about that is, compared to, say, just looking at when your car starts to decelerate in your track data, being able to see the actual point at which your brake pressure spikes is quite useful for knowing exactly when you actually did start braking. So that's one thing we've done, and we've got those for the invert flare, which is used on the older Hondas, so like 1988 through to early 2000s, and then also in bubble flare style, which was used from sort of the mid 2000s onward on a lot of the Hondas. So we've been able to put brake pressure sensors on, like my EK, and then even on the EG Jazz had brake pressure sensor on that, which was cool. And that's fed into just our general like track knowledge and track data from these cars. And yeah, I'm hoping you'll run that setup one day.
That should be easy. I was just doing arts and crafts today with some carbon fiber pieces and a broken instrument cluster to mount my AIM MXM. So that should be pretty easy to add for me as a line. So
you actually get quite a lot of value even just from a single sensor, but of course you can put one in the rear circuit as well. And then last time I was on, we talked a lot about the fits, and we have developed both a GD3 and a GE8, which is the second generation. And with our GE8, we've done a performance camshaft, a 2.25 inch exhaust, and a larger throttle body, pre-throttle body intake pipe system. The car was tuned, and it made, when we got it to 80 kilowatts at the wheels. You'll have to forgive me for talking in metric. I'll try and convert where I can, but obviously the metric units is what comes native to me. I think 80 kilowatts is probably like, I don't know, 128, 127 horsepower on an American dyno, something like that.
That's a miracle for a Honda Fit or Jazz.
Yeah, that's right. I mean, they start around, the 100, 110 horsepower when they're completely standard. And part of that was we increased the rev limit from 6,900 to 8,000. So another 1,000 RPM of usable power band in the top end. And
on
driving the car
rods.
on track. What was that, sorry?
Stock rods?
Still with the stock rods, yeah.
Okay.
So we don't know for sure how long this is going to last, but it's done quite a few events so far, and so far so good.
Usually when they want to go meet Jesus, they do it pretty early.
We did check the piston speed versus what's generally accepted as a safe piston speeds, and we're right on the limit. The L15, like the older D series, is a long stroke. It's a 90 mil stroke. So we know we're pushing things, revving them to 8 grand, but so far so good. And
I don't believe in safe piston speeds, because if you knew what I pushed my K24 to, you would just shake your head.
So you're breaking those rules anyway, are you?
Yeah, by a lot. Formula One wants to know what I'm up to.
Yeah, well, the K24 is also a long stroke motor, right?
Yes, it is. But it takes it. I don't know. I should knock on wood immediately, but
But that's the thing. We just keep doing what we get away with, right? And so we'd sort of modified this and this car, and with the camshafts, it keep making more and more power all the way to 8,000. And so we were sort of thinking, like, what's another thing that we could do to possibly, maybe have the engine combination better suit the higher power band. And one of the ideas was changing the intake manifold to having shorter runner lengths, which is fairly common. Because the original intake manifold is designed for the car when it has its economy life, driving around town. it's designed to have its power band well south of 7,000 RPM. And obviously now we want all the power band in the top end. So on those engines, quite conveniently, the intake manifold's in two halves. So there's an aluminium lower section, and then there's a plastic upper section. And we had the plastic upper section 3D scanned, and then I designed a new upper section that basically put the bell mouse as close as possible to the lower section, shortening the runners as much as possible. And then we had them, and we had one made. The first one we made, actually, I undershot its requirements a little bit, and it imploded due to vacuum, and
Oh man,
a little bit of plastic went through the motor, but didn't seem to hurt anything.
That's
and then
it's a Super D series, right? Like,
yeah, it's a super little robust sewing machine, and
yeah.
So then we learned from that. We designed a new one that was much more like taking design cues from a pressure vessel. It was almost fully cylindrical in profile, has like ribs on the outside and a little bit stiffer. We also changed to a material that is a little bit like stiffer. So we're using what's called a nylon, and the grade of nylon is nylon 6, and that's the stiffer of the nylons. It's actually the same material that the OE plastic upper half is made from, but we were producing our part with SLS 3D printing as opposed to injection molding. And there were some questions as to whether that would be suitable. Like, okay, you might have been able to do a few dyno pulls, but could you actually do a whole track day with a 3D printed part? And we've since been able to prove that to be the case. And the combination of this new shorter plenum, and we also run a K24 throttle body on the car, so it's a 65mm throttle body. And the combination of those factors increased the power from 80 kilowatts at the wheels to 85 kilowatts at the wheels. So got us another 5, which may not sound like a lot, but when you're playing with a 1500 cc and trying to get every little bit of horsepower that you can, it all makes a difference.
I need to go back to this K24 throttle body that's 65 millimeter. Which throttle body is that? Because I bought a variation of, every year TSX, so the K24A2. I bought every variation of every year that I like, grouping of years, and I could not get anything past 62.5 at its biggest.
Okay. Yeah, I haven't got the part number on the top of my head, but I'll be happy to send that to you after this.
Okay. I'm not allowed to. I'm just.
Oh, okay.
They're floating around. If they're floating around, I need to figure out what they are so I don't get my hands on them. So
I know there's the K24 one, and then there's also the J30 one, and then of course J35, and then J37, and they all have slightly larger bores. The really neat thing with those electronic throttle bodies is the plug's the same, so you can sort of swap them in and out. I believe there are some considerations when it comes to like the larger ones draw more current and things like that, but we haven't yet, with what we have done changing throttle bodies, we haven't yet found those limitations.
Yeah, the whole OEM drive-by-wire throttle body life is a little crazy. Do they all have the same vacuum lines, or are you having to block some stuff off or reroute stuff?
They're a little bit different when it comes to what type of plumbing attachments they have. Some of them have the port for the EVAP. Some of them have the EVAP directly mounted to the throttle body. Some of them have coolant lines. Some of them don't have the coolant lines. Some of them have the map sensor directly on them. Sometimes you have to plug that, depending on what you're doing. But generally speaking, those are relatively easy things to do.
Okay. So I personally, I've been seeing the pictures of the funnels. I think those are the greatest invention for a Honda Fit, because
yes,
the OEM engineer is an idiot. whoever placed the oil fill where they did on that car, like, I don't even feel bad for saying that. I know the bean counter probably required it, but it was like, what are you doing? Yeah. Anyway, I'll have to add that to my cart. So
Yeah, it's. I mean, there's some good things, some bad things about the more modern Hondas where they've obviously got this design principle where the engines are more sunken under the windscreen. The windscreens are pushed forward. The engine bays in general are shorter, and from the 2007 cars through to the 2014 cars, when you're working on a Honda in that range, in that age range, it's very obvious that the engine bay proportions are much tighter than the older cars. And yeah, I was as shocked as anyone when we went to start working on the GE and trying to just do a quick oil top up at the track, and there's no direct shot down into the oil cap opening on the valve cover. Like it's completely offset under the windscreen. So that's why we came up with that little offset funnel. And then, like, I don't really believe in charging people for 3D printed things. So we just put it on our website, made it available for free.
Well, I mean, it has to get shipped here, but we're not going down that rabbit hole. So I hosed myself. So I also did it to my own race car, because when you put a K24 in an 8th gen Civic, you have to lean it back to get the header to clear. And I pushed my fill hole on the valve cover too far under the cowl there. So yeah. Now I did it to myself. I engineered myself into that hole. So
I love it. I love those situations where you're like, oh, I've only got myself to blame here.
Yeah. Oh, and when I did it, I also went to an exterior cooler and a deeper pan or a bigger pan. And so instead of putting like 5 quarts in, now I put 9 quarts in. So,
right.
Yeah. Good job, Con. So, anyway.
Yeah. So the development of the G8 has been really fun. I've been using the car. We have a thing in Australia called the D Series Cup, which is like it's a track day. It's not a wheel to wheel racing thing, but it's like in terms of like building a community or having sort of like group of people with the same sorts of cars all turn up at the track on the same days. It's really great for that. And I had been attending those events with that group of people with our D Series cars, and I talked to the guy who organizes it, and I said, look, the Jazzes are now becoming, or the Fits are now becoming the entry level Honda, if you will, and they're also single cam engines, very spiritual successors to the D Series, if you will. Would you mind if we started bringing our Jazzes along to these events? And he's like, no, more than welcome. And so I started doing that, and now they've even broadened out, and they actually market the events to other jazz guys as well. So they're trying to build like a little subclass of jazzes. And at the last event, they had it was like 6 or 7 jazzes in the field, so that was pretty cool.
I think my only regret with the way I can even deal with where they put the oil pickup, but I'm just anti direct injection, so I don't know.
Neither the GD3 or the GE8 L series are direct injection.
Oh, I thought they were direct injection.
They went to direct injection with the L15B, like the turbo motors.
Oh, okay. All right.
Yeah. Yeah. So the L15A1, which is what's in the GD3, and then the L15A7, which is what's in the GE8. Like, the best way to think of them is like D series with K series style crank triggers, cam sensors, and coil on plug, so ignition. So they obviously non-distributor motors, and they don't have the VCT like a K series has, obviously, because there's only one cam.
The other thing I dislike is that I have to remove the valve or the intake manifold to change the spark plugs. But
that's actually, so Honda actually have designed it to make that really easy, and that all you have to remove is that upper section, and it's O-ringed on both sides. So I think it's like 6 bolts, and it comes off. Like, literally takes like 2 minutes once you know what you're doing.
okay, well, I don't know what I'm doing, but yeah.
It was one of those things that, like, before we got familiar with the cars, you think, oh, that's going to be a real pain, changing plugs or changing coil packs or accessing anything on the other side of that intake manifold. But sure enough, Honda actually looked after us, and it's actually designed to be worked on, so it's actually not such a big deal.
Okay. I think, yeah. So the other question I have is, when you made some adjustments to your intake manifold, right? Were you using any software to do that, or were you just working off of like engineering and fluid principles?
So when the first one collapsed, because it wasn't stiff enough to resist the internal vacuum, we then used FEA, which was like a static simulation of vacuum being applied to the internal surfaces of the plenum, to then validate the stiffness of the second revision. That's not simulating fluid flow, that's just looking at the strength and the stiffness of the part. So we did use computer-aided software for that, or computer-aided tools for that. You can't really use, well, at my level, and keeping in mind this is just something I'm working on after work, you can't really simulate the engine dynamic airflow very easily. One of the biggest challenges is you'd have to have an engine and then fully instrument it to find out what they call the boundary conditions. So what the pressure variations are at the inlets and outlets of your plenum, and then you then use those informations to set up your simulation so that your simulation is accurate, and then you can then in theory you could make iterative design changes to your part in the simulation. But that's just beyond the scope of what we were doing. So for us, it was more make a big change, going from the original runner length to making the runners as short as possible, and then seeing if it made a big difference or if it made any difference. I don't think we completely nailed the runner length. I don't think they're perfectly tuned to the rest of the system. I think, well, we actually did test increasing the throttle body size independent of changing the intake plenum, and the power gains from just increasing the throttle body size were pretty significant, possibly on the same order of magnitude, if not more, than changing the plenum itself and changing the runner length. So either way, we're talking about 2 to 3 kilowatts, sort of 3 to 5 horsepower kind of thing. A lot of people have asked me if I would sell those plenums, and the answer is no, because I don't think that for what they would cost to manufacture and produce and sell, the 2 to 3 kilowatts is not, doesn't really make sense. it was worth it. It was worthwhile for me as a cool little mini project and as a learning exercise. But the actual power gains weren't that significant.
Yeah, I didn't realize it was just like a side hustle. I didn't, or a side project, not a hustle, side project that you were just doing for funsies, to go through the motion and to learn, right? I mean, we all get inquisitive and we look for something to do to educate ourselves. So
there was a small chance that there was an outsized response from the engine. Like, let's just say it picked up 10 horsepower. And then it would have been really cool to share that information with the community, and people could have come up with different ways of maybe more cost-effective ways of making this change. And then the whole fit community could have benefited from that knowledge, but that wasn't the case. That's sometimes how it goes.
Yeah. How big is the Jazz Fit community in Australia?
It's probably the fastest growing in the Honda world, where there's Facebook groups, there's cruise groups, there's, like I mentioned before, where people are now getting invited to attend track days and motorsport events. So it's as the 10 years ago, you used to be able to get an EK for $2,000, and it was in reasonable condition, and all of the radiator hoses and all the plastic parts were still fine, and they weren't brittle, and the wiring looms were still okay, and that type of thing. But in 2025 or 2026 now, that's just not the case. Like, you're getting really, really worn out cars in an EK, really, really worn out cars for $5,000, or cars that have really damaged paint, and it's hard to then doing things like fixing paint or just fixing sort of boring components, non-performance parts of the car, just so you can then modify it for performance, is sort of detracts from the ease of being able to just pick up a car and then just immediately get into, your coilovers, your wheel install, your exhaust, blah, blah, blah. And that's what happens when the chassis gets older. We saw it happen with EDs and EFs and CRXs, and then with EGs, and now with EKs. And that's just sort of what happens when time progresses. The cars go from being the one that you can pick up relatively cost effective, or pretty cheaply without having to save up for a long time, and they turn into more of a I really want an EK, and then you'll go out and find that EK, and then you'll spend the time to make it the way you want it. Where Jazzes are now, or Jazzes or Fits are now in that category of I can pick one up. It could be a second car or a third car. It can sit outside, and I can use it when I want. That type of thing.
Yeah. Well, they're still not really cheap here in the United States for that. I mean, 200,000 miles and they still want $5,000 or $6,000 for them. And to me, you can get the same 200,000 mile FA5 or FG2, the 8th gen Civics, for that price almost. So yeah, you are rolling the dice. You can guarantee that a cheap Civic Si has been over revved and all that, but they pretty much take it, right? Yeah. So it's just a dichotomy here that's really weird, where the Fit Jazz is almost as expensive as what was the performance car of that era from Honda.
I think we touched on that last time as well, and I said the same thing. It was I didn't quite appreciate that the Fits were sort of disproportionately still holding their value in the US compared to here. But you're absolutely right about some of the other 8th gen cars now representing actually better value, especially when you take into account if they're already a native K series. And on that note, along those lines, we recognize that as well. And in our particular market, the 8th gen that currently, or even I think this goes for out of all the Hondas, the one that represents the best value for money right now is the European engineered, the FN2 Type R Civic. So the 2008, the shorter, the two-door Civic. You're familiar with that model?
Yeah, I am actually. I was looking for a brake, the ABS module out of one of those. But
so in our market, they range from 8 to 15,000 Australian, whereas the FD2Rs, so the four-door sedans that we're fans of, the Type R model in that for that variant, they're more in the $30,000 to $35,000 mark, so over twice the price. And it occurred to us, like, why is there such a difference? Like, why is one valued highly and then one's almost not valued at all? They both have K20s, they both have 6 speeds, and so seeing that these FN2Rs were sort of slept on, we thought, well, we should pick one up and sort of see what we can do with it. And so we did that. We purchased one about 3 or 4 months ago, and since then we've been able to get a really good understanding of what they are and how they compare to the FD2R or the FD2s, which we also have. So if you've got any questions up on that, otherwise I can start talking about some of the differences between the two if you're interested.
Yeah, I'd love to know the differences, because that price differential is kind of crazy to me.
So our FN2R, so this is the two-door. It, with the back seats taken out of it, weighs 1,203 kilos. Our FD2, with the back seats taken out of it, sort of partially stripped, aftermarket wheels and so on, weighs 1,280. So it's about 80 kilos heavier, the four-door. In stock form, the FD2R's K20A makes about 10% more power on paper, but the K20 Z4, which is in the FN2, with an intake, exhaust, and a tune, you can match that. So our car, now that it's been tuned, makes that same 10 to 11% more power. The FD2Rs come with an LSD, so obviously there is some premium associated with that, and our FN2 doesn't, or they commonly didn't. But adding an aftermarket LSD is not the end of the world, and it also gives you the opportunity to go for a clutch type as opposed to a torsion, which, if you intend to use the car for motorsport, you're probably better off with a clutch type anyway. And that's our plan. So we have a one-way Cusco clutch type to go in our car. The front suspension design, they're both McPherson strut, very similar. The lower control arms design is the way that they're attached to the chassis is slightly different. I would say the FN2 is superior, and the reason for that is that in the FD2, how you have that, similar to like a TSX, it has that one lower control arm bush that's 90, like it's orientated 90 degrees, like the axis of the bush is up and down.
Yep.
Those bushes tend to have, I think, especially when they're worn, like a lot more compliance than the bushes that are orientated the other way. So that's one big difference. The FN2R also has aluminium control arms. I think maybe the FD2R probably does as well. Where the two chassis really differ is in the rear suspension. So you possibly would have heard that the FN2 has a twist beam like a Jazz, which is like a bigger version, and the twist beam is without a doubt technically inferior to a multi-link. However, us having just come off 2 years of developing the Jazz platforms with the twist beam, we have a pretty good idea of what to do with those now. And while they will never probably be as good as a multi-link, you can still reduce a lot of their downsides, if you will. So the main downside is that you don't get any camber gain with suspension compression. So whatever your static camber is pretty much more or less what you get all the way up through the travel range. Whereas you'll know with your FA and with my FD2, even just once the car's lowered, you get quite a nice amount of natural camber, and then as the suspension compresses from there, you actually get more camber gain, which helps keep the tire presented to the road for maximum grip. However, what you do with an FN2 is you use like fixed shims, and you can shim it to have the camber that you want. However, it's compromised in that you have to shim it for the camber and toe that you want. Almost like you have to think about it as putting the camber in like the maximum amount of camber you want, because it's not going to gain any more camber as the suspension compresses or as the car rolls. Whereas with our FD2s or FA5s, we can run slightly less static camber, and we can rely on that camber gain in the rear suspension to give us more camber in the highly loaded situations.
Yeah. So the multi-link thing is kind of, I don't track my fit Jazz. I just drive it to work like 150 miles a day. But that torsion setup, that beam in the back, I mean, we have guys in the United States who are bending theirs to get more camber in. Like that's a thing, is to bend the bar to get camber in the back.
Yeah, so with a GE8, the GD3s you can shim, FN2s you can shim, GKs you can shim. For whatever reason, Honda in their wisdom decided that on the GE8 that they were going to weld the spindle to the twist beam and make it not able to be adjusted. Okay. So you can bend them like you said, or in our case we cut and welded the we built a fixture, we put the beam in the fixture, and then we sliced a section out of the beam, and then we manipulated the spindle, and then we welded it back up and increased our rear camber to about -2.8 or -3 degrees. That is a bit of a pain. That's definitely pretty far from a bolt-on modification, and no alignment shop's probably going to do that for you. So obviously with the FD2 and the FA, you don't have to do that. You can get an adjustable camber arm, and it's easy to set your rear alignment settings. So they've got an advantage there. Another key difference is similar to the fits. The FN2 has the fuel tank under the driver's seat and under the passenger seat. And while that's great for mass centralization, it has the effect of it impacts the seating position, and it makes it hard to get your seat like really low, and it puts you in a slightly different position compared to the other 8th gens. You can work around it with like we make these fixed bucket seat mounts that don't have a cross beam. Oh, sorry, only have a cross beam at the front, and that allows you to push your seat really down and backwards, and that pretty much makes it a non-issue. But you can still feel it. Like if you jumping from the FD to the FN on the same day at a track day, I could feel the difference in how I was sitting. So that was interesting.
Yeah, you're definitely not going to be able to lower the seat. There's a lot of tall folks that when they track their fits and Jazzes have a problem with that, like, close to the roof kind of thing. So you're not going to be able to do the like Miata floor pan drop so much.
No, you definitely can't win the fuel tanks underneath. But yeah, so it's interesting to see where they're similar. It's interesting to see how they're different. I guess my takeaway is that both have pretty high potential, and as long as you know how to. So McPherson Struck cars are less tolerant of how you set up the coilovers, and that's because the motion ratio is high. So when you run high spring rates, if you don't run a helper spring, you will end up with, and if you like preload your spring or even just have zero preload but a high spring rate, you'll end up with very little droop travel. And the same thing at the rear with the twist beam. The motion ratio on the FN2 is 0.8. So again, the same kind of thing when you're running the higher spring rates. Unless you consciously compensate for this effect, you'll end up with less droop travel. And by comparison, older cars like EDs and EFs and EGs, because they had their lower motion ratios, even if you ran high spring rates, you still ended up with, let's just say, 30 to 40 mil of droop travel. Whereas on the newer chassis, if you applied that same coilover installation approach, you might only end up with 20 millimeters of droop travel. Where that makes a difference is in the damper's ability to, well, one, the wheel's ability to follow the track, and two, the damper's piston travel and ability to move. Damping is related, like your damping force is related to the damper's piston speed. But if the piston is hard up against the top of the inside of the shock, when an extension, if the piston if it only has a little bit of possible displacement before it effectively tops out, you're going to get very little rebound damping from that, because the piston doesn't have enough room to actually travel to then get to the higher damping forces. So the approach that we take is we make sure that even with these higher motion ratio suspensions, we make sure that we still are setting them up so that we have at least 50 mil of droop travel. And that's, again, partially about what the tire's doing on the track surface, and partially about what's happening with the damper and allowing the damper to have, like, allowing the piston to be able to actually travel within the damper before it tops out.
I just pulled up my sheet, and it looks like I'm right around 43 millimeters of droop in the rear of my car.
Yep.
So, and it doesn't droop as much as I would like it to.
So with our FD2, the rear springs go completely uncaptive, and they can in theory rattle around. And what we have is what we call a spring retainer, which is a little aluminium boss which sits on the lower control arm, and it basically puts material inside the spring so that the spring can't kick out sideways. On our FD2, we're running an 11 kg rear spring. So, and compared to you with, if I believe from the last time we spoke, you're running a 7 kilo rear spring or equivalent. If we set up our suspension the same as yours, we would have like 15 mil of rear droop.
Yeah, I mean, this is the trick with, I don't know what voodoo is going on with my car, to be honest. I just know it's working well right now. I mean, it's working well enough that I don't want to upgrade my dampers, even though I really want to. I fear that upgrade, right? I don't want to set it backwards. But I also don't run my car like everybody else. Everyone runs a really stiff rear, and I just don't.
No, you don't.
and it seems to make my car work the way it is. Now I have like a reverse stagger. The rear is lower than the front. It has all sorts of stuff, but it just seems to turn the way I want it to right now. So,
and that's why I think I always try and say at the start, like when you and I talk suspension, that I would never insist upon you changing anything based on something that we discuss, because it's working for you, and far be it for me to say change it. But also, like, you show an interest in talking about different suspension ideas and different methodologies. So without needing to imply something's right or wrong, we can still talk about different approaches.
Well, okay. So, I mean, you said 18 Hondas that you build parts for. I'm assuming you've worked on basically all of them, right? Or have a shop car or a customer that relies on you heavily for all those cars. So when I understand what frequencies are, at least I think I do. But when you set up your car, okay, first off, you also sent me my frequencies for what I have, right? And when I read that and I went to the internet, it was like, oh, those are F1 range frequencies. And I'm like, there's no way. Get out of here.
Your front one in particular was quite high.
So it's, to me, it's there's a lot of talk about it, and there's a lot of talk about motion ratios, and we've sort of talked about that in the past on this podcast about doing the measurements and all that stuff. And you have all these cars. How is the frequency informing you when you're setting them up or looking to design parts?
Awesome. I'm aware that I've probably been railroading you a little bit and talking quite a lot, but I'm going to continue that with this. I'm getting into suspension frequency. So I'm going to give you a little bit of background.
Sure. Yeah.
And then it's going to be a bit from me, and then we'll discuss it and go back on topics when we get to the end of it. So suspension frequency as a concept actually dates all the way back to the 1930s, and it was pioneered by a General Motors engineer. So certainly by no means something that I've come up with by myself. Suspension frequency is a quantification of how fast a car's suspension bounces, and it can be measured. So you could have potentiometers on the suspension of a car, and then you could log that information, and then you could do a frequency analysis to determine what the suspension frequency was for any given bit of time or piece of track or something like that. So you can have like a measured suspension frequency of what the car is. But you can also have a theoretical value, which comes from a mathematical formula. And that's what we're talking about that's what I've been talking about when I've been talking about calculating your suspension frequency. It's your theoretical suspension frequency. And that formula it's 1/2 pi times the square root of wheel rate divided by mass. I would encourage people to look that up independently. They can see the formula. They can sort of understand what the inputs are.
And then you're going to regret skipping math class. I'll tell you that.
It is a little bit of maths, but it's very achievable. It's very achievable. You can definitely get into it. HP Academy has some excellent resources on this. In their suspension course, they break it down in detail as well. So, yeah, like I mentioned, when it comes to doing the frequency formulation for a car, we want to be talking in wheel rate, and wheel rate has to be calculated as well, and that the input for that is your suspension motion ratio and your spring rate. And all this is taken into account. There's some effect of this is that you can compare the stiffness of cars with what it allows you to do is compare the stiffness of cars with different axle weights and different suspension designs with those variables accounted for. So we can compare the stiffness of a double wishbone car with 1,000 kilo, total vehicle weight versus, and 65% of that might be on the front and 35% of that might be on the rear. And we can compare that to a car that weighs 1,200 kilos and it has a max truck front suspension design. And so that's what this approach is all about. So when it comes to anything car related, there are a lot of different ideas floating around the ether. This is particularly a thing when it comes to suspension, because unless the body of the car is resting on the tires, the car will still drive. So people can have very different suspension can be set up like completely differently. And unless the tires are physically locked up in some way, the car will still drive, and someone could probably still convince themselves that they like the car that way, if you sort of know what I mean. It's the suspension in and of itself doesn't really stop the car from driving, so there is a lot of room for different setups. And because of this, things like the placebo effect can be strong, or personal bias can be strong. And that's why I feel it is important to measure things wherever possible, and otherwise take approaches that are not based on feelings if you can. There are some things when it comes to suspension that can be measured easily with simple tools. An example of that would be like bump and droop travel. So two different people could have two different approaches to suspension set up two different cars, and then a third independent person could physically measure the bump and droop of each car, and everyone should be able to agree on those numbers. This only requires a tape measure. If that independent person measures your your droop travel as 43 millimeters, there shouldn't really be any need to disagree on that. Are you sort of following me so far?
Yes, sir.
Things like ride quality, under and oversteer balance, turn and feel are much harder to measure. And they don't have standardized metrics or scales that everyone agrees on.
Yes, the quantitative versus qualitative stuff.
There's no like, oh, this car has a 3 understeer value, and everyone goes, yeah, well, this one has a 4 and that one has a 2, and I like 3 and he likes 4. It's unfortunately, as much as an engineer I wish it was like that, it's not like that.
No, it's subjective in those areas.
It's subjective, that's right. So suspension frequency is one approach that can be used that I like, because it is a repeatable method that I can use on multiple cars, and it doesn't have any. In that formula, there was no input there for driver's feelings, right? So that's what is good about it from an engineering perspective. It also has a long-term established scale, and that what I mean by that is over the years, like businesses and engineers and all sorts of different people have calculated the suspension frequency for the various cars they've worked on, and based on that, people have found what tends to work well in different applications. So for passenger cars, they say, a recommended ride frequency range might be 0.5 to 1.5. For sports cars, it might be 1.5 to 2. And for sports cars, it might be 2 to 3. And for track cars, it might be 2 to 3.5, that kind of thing. And lots of other people have sort of set their cars up within these ranges and sort of verified, like, yes, this is a track car. We have suspension frequencies in the 3.2 range, and the car works pretty good. Like, it's not just you within your own bubble trying to decide what the spring rate should be, or whether the car's stiff enough is probably a better way to put it. I think one book that talks about this is Carroll Smith's Turn to Win. I think that's where I first was introduced to the approach. And he has these ride frequency ranges in that book. And I think probably tire technology, like since he published that book, tire technology has improved to the point where we are probably running our track cars a little bit higher in the ranges compared to what he had originally sort of identified. And yeah, I attribute that to improvements in tire technology mostly. So what I mean by that is, like, in his book, he might have put sports cars at that, 1.5 to 2.5 hertz. We're running pretty much all of our cars between 2 and 3.2, for an example. So the first Honda I modified for motorsport was my DC2 way back in the day. And I calculated its suspension frequencies, and then I had those in a spreadsheet along with its corner weights and alignment settings and all sorts of information related to how that car was set up. And then over the years, I basically, for every car that we get, I do a similar thing. I have a spreadsheet for it. I check its suspension motion ratios. I check its corner weight, and then I work out its suspension frequencies. And then in recent years, I've then been using that to help me order my coilovers in advance. So when we bought the FN2, it came to us on standard suspension, basically an unmodified car, and I was able to put that car on our corner scales, measure its suspension motion ratios, use a ride frequency target to back calculate what spring rates I wanted, and then I could even go a step further and work out whether I needed helper springs or not. And then I was able to place my order with the coilover manufacturer with all of those specs. So I was able to tell them what spring rates I wanted. I was able to tell them I wanted helper springs, and they were able to build those and deliver them to me right from the start, all basically according to my requests. And then when we put that in the car, we knew and we found that it was about as stiff as all the other cars that we know and that we have and that we have previously tracked that have suspension frequencies in the same range. And because we're running similar tires on all the cars, that tends to work quite well. One concept that has to be discussed with all of this is something that deviates from strict engineering into more philosophy, and that is how you think about setting up the car in a more holistic way. And this is where it becomes my opinion and not something necessarily out of a book. To me, it has never made sense to use the ride stiffness at one end or the other of the car to affect its understeer or oversteer balance. And my justification for that is that the sprung weight's impact on the tire is more indirect than variables like tire pressure or toe angle or camber angle. And I'm not looking to, because I have those more direct variables to tune my understeer and oversteer balance, those are typically what I use. And I don't typically look for my ride springs to tune my understeer and oversteer balance.
Yeah, I would agree, but I don't think a lot of people agree, right?
Yes, yes, that's right.
So I don't think it's controversial to say it. I think it's one of several schools of thought. Okay.
That's a great way of putting it. Yep.
And it can work for people. It's worked for you. It's sort of worked for me. I don't know what school of thought I'm in, but to me, it makes sense that the way we set up camber, caster, toe, and tire pressures, those are pretty hard measurable items, right? And then we can do smaller tweaks to make things happen. And the spring rates, in my opinion, are how compliant the car is, not necessarily how it turns. But one of the reasons I'm at a lower rear spring rate is because at higher spring rates, the car doesn't like curbing, and I run at tracks that require me to eat curbs all the time.
Yep.
So I need it to be compliant, and then I need it to turn also. So
yeah, it's perfect. It's perfect that you said that, because as a driver, how you know, like what I do to know whether the car is stiff enough is I look at it, or I evaluate its heave and its pitch. So it's like front to back pitch, its roll, although I keep in mind that the ride springs only have a partial effect on the roll stiffness, because we also have sway bars and geometry helping us there, or that can contribute and combine to provide the total roll stiffness. And then, like, this is not typically relevant, but would be in some cases, like if you had a speed dependent downforce. So if your car does have it, does the chassis ride too low at higher speeds? That would then feed into whether your spring rates are stiff enough or not. And then how you would sort of maybe judge if it's too stiff would be things like, and this ties into what you just said, harshness when hitting curbs. So if you feel like the car's getting unduly upset when you're riding curbs, or you're lacking the confidence in hitting the curbs, and maybe for your particular type of track, like that's where a lot of lap time is, and it just needs to be able to do that. So harshness when hitting the curbs, or being unable to just feel the weight transferring under brakes. And if you just had like an abrupt sort of non-driver induced under or oversteer, and you couldn't attribute that to some other reason like cold tires or something like that. Yeah, it's interesting. It's interesting that you mention curb compliance and how you feel that, or how you think about that with respect to your rear spring rate choice, but then your front rate is so stiff, which would also, presumably, if your fronts are also hitting the curb, would maybe be not as logically consistent with what you've done at the rear. But perhaps the way that the car reacts, like when it hits at the front and then how it absorbs it at the rear, maybe that just all works out.
That's generally how it works, right? The front seems pretty compliant and tolerable over curbing. It helps. That we're going back to feeling, right? Okay, so it's all I've got for you today, and it turns in fine. It mounts curbs fine. It was dismounting curbing where the rear was the worst. It would soak it up, but it would launch me off. Once that damper let go, it was almost unpredictable.
So let me ask you a question. Do you have helper springs on the front of your car?
I do not.
You don't?
Nope.
So how much front droop would you have?
Almost another 50% probably than the rear. And let me pull up my sheet. It is like 70, let's say 70 millimeters of droop up front.
You may want to double check that.
Okay.
Because I don't see how that would be possible with your spring rate.
Okay. Yeah.
Without a helper spring.
Yeah.
So let's just say, like I've got this spreadsheet number here. Your front corner weight will be something in the range of 335 to 340 kilos.
Mm-hmm.
And you've got a 17 kilo front spring. So 40 divided by 17, you'd have about 20 mil of droop travel without a helper spring. Because the front motion ratio is close to 1, right? And so what that means is that when you hit that curve, the front your front wheel is like, let's say it comes off the ground, it can't extend very long, can't extend very far, and the damper doesn't have very much travel in order to provide much damping on those front corners or on that front inside corner. And then that may translate to instability of the whole car. And then maybe there's an interaction between the front and the rear there. I mean, I'm speculating here. But it just goes to show that I think what makes cars particularly challenging is how interdependent they are. Things front to rear, like sway bars are the perfect example. Stiff rear sway bars tend to, from the driver's perspective, improve turn-in, which you're actually making a change on the rear axle, but it actually helps something on the front axle from the driver's perspective. And there are other independencies like that.
Yeah. So other people have tried my combination on their car just in other 8th gens.
Yep.
And they're like, this is garbage. And then when I bought my 8th gen, it ran what everybody else runs. It was running.
Everyone except for us, for me.
Oh, you don't run it that stiff? They were running, probably 22K rear springs. And then, let me look, 10K front springs. That's what they were running in these cars, still running in these cars. And I would melt the front tires off my car. I also don't run a front sway bar. I don't believe in them. I think they're the devil. It's
okay. Let's dig into that.
Okay.
Why do you believe they're the devil?
Because when I tried to run it, it felt like the front end was sliding a lot, and I don't want my front end to slide. And in pictures, it looks like my car is like pogoing off the outside tire and lifting the inside front tire.
Right.
And then,
But because you've got very limited droop, there's something else. There's another variable that you've changed there effectively compared to a standard car that reduces how much independence you have on your front axle. So I would argue that the effect that you wanted to achieve by removing the sway bar is sort of counteracted by not running any droop travel, or very limited droop travel.
Okay. I mean, I just ordered a new 120 rear bar because I was on a .095 because I'm hoping I just want a little pre apex rotation. That's all.
Sway bars, I think what's really important with sway bars is that they are considered to be a mid-corner tuning tool primarily. At the very instant that you go to turn in, the sway bars rates, both front and rear, is almost negligible because they need that. There needs to be some roll. There needs to be some weight transfer for them to start to generate a significant rate and actually start doing something. And the way that I sort of look at it is that if you need to be getting it's ideally that you would get your rotation right up from turn in and then carry that rotation. So you've got your maximum amount of rotation at mid corner, and then obviously from that point you're back on the throttle and you're accelerating out again. It's probably a little bit different in Australia. Our tracks, we tend to have tighter corners. You guys tend to have more sweeping corners, which makes sway bars more relevant for you guys and less for us to some degree. Obviously, it's track dependent. Like the track that we go to most is Winton, which is a relatively small track, only really has one sweeping corner. We do have other larger tracks like Phillip Island and SMSP that have more sweeping corners, but they're still not really like the American tracks, which have a lot of sweepers. Possibly that's where our experience sort of differs a little bit. So your car, with your 17 kilo front springs and your 7 kilo rear springs, you have a front ride frequency of about 3.4 and a rear ride frequency of 2.4. And that is quite a large difference. Mm-hmm. So the two things you would think from that is, one, it's quite a large difference. Two, the front frequency is quite high. Being over 3 is pretty high indeed. And the relationship is obviously front stiffer than rear. I say we've covered that. How I set up our 8th gen is with a 12 kilo front spring and an 11 kilo rear spring. And that resulted in a 2.8 front ride frequency and a 2.9 rear ride frequency. And if we apply those same sort of observations looking at that, so they are relatively, those front and rear stiffnesses are closer together just in general. And I've gone for the rear being slightly stiffer, and they're both under 3. And then if we were to look at the case that you talked about with the, let's call it, just for the sake of another, like a better description, let's call it like the traditional 8th gen setup, where they're running a 10 kilo front spring and a 22 kilo rear spring. Their front ride frequency would be like 2.5 and their rear would be 4 or 4.1. So they're doing, and this is a great example of 3 different, completely different setups, but all still drive, and probably the drivers of each all like them. But it just makes this so hard to sort of, again, there isn't really necessarily a right from wrong. I think you could put these 3 cars set up like this all on track at the same time. I think ultimately their lap time would be dictated by the weight of the cars, how much power they have, and how well they and their tires and what tires are under them. I don't necessarily think ride frequency or how the suspension is set up would necessarily impact their single lap pace. However, like you brought up, which I think is very relevant, is if you're doing longer duration events and things like how well the cars look after their tires start to become into it, because sure, on a single lap, any one of these setups could be or is fast, but then when they do 20 laps, how are they, what condition of the tires are in, so on and so forth. I think if I had to speculate, I would say some of the really high rear ride frequency stuff comes from, or really high rear spring rate comes from just a philosophy. And this is again where we go from engineering to philosophy, but a philosophy that the rear suspension of a front wheel drive car is really just along for the ride. You quite often hear that. And so put a really, really stiff rear spring on and basically have the rear suspension have very little compliance, and then just drive it like that. There would be a lot of, there'd be heaps of examples you can point to of cars set up that way. I've never found the need to go to that extreme. I've always found that I've been able to have the cars have all the rotation, or have as much rotation as I need, and meet all those other stiffness metrics that I talked about without having to go to such extremes. And because it's logically the follow approach of keeping the car as soft as it can be while still being able to do what you want it to do. That's why we tend to remain softer in a certain degree. Yeah, do you have any questions about that?
No, I think so. Tell me if I'm wrong. My takeaways from this is that frequencies help you when you do the legwork to initially set up your spring rates, which a lot of people use motion ratio, but motion ratio is part of this frequency calculator. So or calculation. So you're using it to say, I want to be in this zone. What do I need with all of the math to get me in this zone? And then it also helps us compare, like we have between, let's say, your DC2 and then 3 setups on 3 different 8th gens, right? So we can compare setups, and it doesn't necessarily mean one setup is wrong. What it means is, from what you're explaining to me, is that there's something wrong in my front, not geometry, but how the coilover is set up, possibly, for me to run that high.
I mean, yeah, not using the word wrong, because I'm not trying to criticize it or anything like that, but just when you went to the higher spring rates, because you didn't necessarily work with a constant droop target, you made 2 changes at once. Let's say.
Okay.
Like let's say I don't know what spring rate you used before you went to the 17 kilos, but let's just say you had like 10 kilos or 12 kilos in the front, and then you went to the 17s.
Mm-hmm.
If when you did that, because you didn't install a Halber spring, or you didn't set the coilover up to have the same droop travel with both spring rates, you've effectively made 2 changes at once.
Okay. I mean, I'll be honest. I'm totally not against taking a big chance, and when it works, just sticking with it, right? Like, I'm not an engineer, and I don't know what I'm doing, but when it works, I want to keep it working, So.
I think, like, what you could do is you could go, like, you could buy some Halber springs, because they're pretty cheap. They're like $100, and you could install those in the front, and you could check your front. You could check your front droop travel, and you could check your rear droop travel, and you could set them up to have some degree, or some amount. I recommend 50 mil, just because it's a nice number, but it could be whatever.
up front or all the way around?
I think I would say help springs in the front because you will need them. Otherwise, your springs will be quite uncaptive. And then what you've done, and then you could test the car, and then without having changed your spring rate setup, you've just made the single variable change of increasing your front damper, like your front droop, which increases your front damper travel. You've then given your front dampers a better operating range that may just improve again how the car responds when you hit curbs. And then as you work through this, then you might be able to go, okay, well, now I might be able to experiment with different spring rates in the future. But this stuff is, because there are so many variables and because they are intertwined, it can be hard to untangle this, like what's the next best move to use, or how do you sort of get these things straightened out. I think that whether people can have vastly different philosophies on suspension, but surely they could agree that allowing the wheel to actually move is a good thing.
Yeah, so I agree. And I think that's where when people go to these huge rear spring rates, they're not allowing the wheel to move in the back. They're trying to lock it in place. They're not using the geometry to their advantage. Somehow they make it work. I know they lock it in place and then they use tire pressure mostly, at least for the front wheel drive cars. But anyway, yeah, it's philosophies aside, like the frequencies are there, I think, to help get us in the range we want to be in and then to be comparable to other folks. So, and I think that's the important takeaway of our conversation is that it's not the end all be all, right? Like we're not.
No. I wouldn't never frame it that way. I would never say that you couldn't develop a car to be fast with a different method. And like you said, like if you did use the ride frequency approach and that then gives you an initial setting and then you may experiment with going up or down on spring rates, that's totally fine and valid approach.
Yeah. And it's one of those, it's a tool in your toolkit, right? And it's, in my opinion, having to do motion ratios and measure and do all this stuff. And you don't actually have to use the formula. They have calculators for it, assuming you took all of the correct measurements and you did it as precisely as you can do it. You don't even need the math, right? It's a tool in your toolkit to evaluate where you are, right?
For all the common, like for all the Honda chassis that we have, we've got like posts on our Facebook page and on our Instagram of the motion ratios that we measured, so you can get that information from our resources, and then, like you said, you can go and plug that in to an online calculator. I know, again, HB Academy have an online calculator for it,
right? And
then you don't really have to understand the math in the background. And I think what we touched on and what is important is that there is spring rate choice and how stiff the car is, and then as a completely separate thing, there is your wheel travel.
Mm-hmm.
And depending on how you set your coilovers up or don't set them up, you can actually be making two changes at once without really thinking about it. And to try and help people with that, because it's something I've noticed, particularly as we've been getting into these newer chassis with their McPherson strut and twist beam suspensions or their higher motion ratio suspensions, that how you set up your coilovers is very important. Quite often you'll see people say, preload your spring a couple of turns under the spring collar and then set your ride height with the body adjustment. And if you do that, you unless you're very lucky, you can end up with these, setting your car up with, no droop travel. And then you can end up blaming the effect of that potentially on something like a sway bar or some other, because you didn't really understand what you did there, and then you push that onto some other handling thing. I'm not saying that's what you did. I'm just saying that could happen. So what I've done to try and help people set up their coilovers is I've made a one-page sheet with a template that you can fill out that shows you how to measure your wheel droop travel and your bump travel, and it gives you like a little box you can fill out. You can do your before and your after, and that's available as a free download from our website. And I'd recommend anyone who's doing a coilover installation or even on an existing car to go through that exercise just for themselves. It takes a few hours, but it doesn't necessarily cost anything. And what that also feeds into is another common problem is incorrectly set up bump stops. So, for example, both on the back of our Jazzers and on the back of our FN2s, the coilovers that we bought and installed, as we installed them, the bump stops did not engage at all. So if you took the spring out and you jacked up under the end of the beam, and you jack it all the way up until the tire hits the body, the tire will hit the body and the bump stop will still have 30 or 40 mils of shock shaft before the bump stop engages.
And that's where the bump stop packers came from.
And that's where the bump stop packers come in. Yep.
Yeah. Okay. I was like, where did this come from? Like, I mean, I get it, right? You don't want to buy more or disassemble or whatever to get more, to put in a new bump stop. I know guys that ride on the bump stops. I mean, we all have deficits in our life, right? Especially with our suspension.
There's no. Most of my cars ride on their bump stops, but I run a tapered bump stop. What that effectively does for me is it gives me a progressive effective spring rate, because the bump stop spring rate, if you want to call it, combines with your actual linear spring rate, and then those two things work together. Some of my cars are so low that they might only have 30 mil of total bump travel. So in order to actually fully arrest the wheel in time for control arms and other things not to hit, you have to have the bump stop pretty much almost already engaged. I wouldn't say that's necessarily a recommended approach, but that, like the car I'm mostly talking about here is my sedan, my EG sedan. It runs 18-inch wheels. It runs very low ride height. Mm. I've sort of engineered that to work, but you probably, for a pure, like if you were actually racing, you probably wouldn't necessarily set up a car quite that compromised. But yeah, what you've got to sort of think about is the coilover. When you order your coilovers, like, they don't know what size wheel you're running. They don't know what offset you're running. They don't, like on the older cars, they don't know what upper control arms you have. They don't know what camber setting you're running. They don't know a lot of things. And so while they've done a great job of producing their coilover, and it's how they've set, like what they've set for the body length, and what they've given you in terms of a bump stop just may not suit your specific application. And if you're driving around on the street, you may not ever really notice these effects. But if you're really pushing the car hard and like hitting curbs and really at the limit of the tires, it pays to know that your specific cut, like what your wheel, what your droop travel and what your bump travel is for your specific car. And it also pays, in my opinion, to check that you're not getting any mechanical binding of hard parts like control arms and or knuckles before bump stops engage. A good example would be the CL9 or the TSX platform. Due to how the suspension is laid out on that, the knuckle if you're running any kind of track style front camber values, the knuckle will actually hit the spring quite early on in the bump travel range, and that will then side load your coil over and possibly lead to damaging it. And yeah, you've got to use bump stop packers or a bump stop of the correct length to stop that from happening.
Well, I'm glad I don't have that problem, because I would swing and miss with that. I was just thinking, those sheets that you have, to set up your coilovers, I think you're just trying to get me out in the garage in the we're in the dead middle of winter here. It's below freezing for sure. So, everybody knows what country you're in, below freezing is. And I really don't want to sit on the concrete and do this, but I might have to find my problems. So
grab yourself one of those gas burning heaters and do a little bit on it. But yeah, obviously we covered quite a lot. I feel like I talked a lot, but hopefully you found it interesting.
Oh, I did, but now I don't want to say more questions, but more things to research and figure out what's going on. But, as long as my car works, I probably won't do anything. So I'm definitely afraid of adjusting the voodoo on this car right now. So anyway.
Yeah. And unless you had a really good reason to necessarily go and do it, but yeah, without, you could actually check that droop, how much droop you have front and rear, without actually pulling anything off the car. All you need to do is measure with a tape measure from your hub to the guard with the car on the ground, and then jack it up from the sill, and then just see how far the wheel falls down, like droops down, and then measure that same hub to guard measurement again, and subtract those two numbers, and there's your droop travel.
So that's what I did. I'll do it again, and I'll send you the numbers on the side. But I find that the design of the 8th gen Civic front arm doesn't help. It bottoms itself out. There's only so much droop that side will, or that front will have. That compliance bushing is trapped inside the subframe, and the arm stops inside the subframe. So that's true, but I would imagine your what's limiting you from a droop perspective right now would be the body length of your coilover. Okay. I'm gonna get the sheet. I'm gonna put like a heating pad on the ground, torpedo kerosene heater pointed directly at me, and then I'm gonna do this.
You would have seen how people get like a sleeping bag, and you unzip the bottom, you have your feet hanging out.
Yeah, just like that. So that'll be me.
Oh, very good.
Trying to do measurements. Grant, it's been a pleasure. We're an hour and a half plus in. We're probably buried the lead here, but obviously, where can people find you and the website and all that?
Our website is honeddevelopments.com. You can find us on Instagram at honed_developments. You can find us on Facebook. You can find our email on our website if you want to email me any questions. Thank you again for the opportunity. I'm always happy to chat about this stuff. I guess I should take pains to say that some of the things expressed here are my opinions, and I'm not trying to put down anyone else's approaches or anything like that. You simply wanted to have the opportunity to discuss this stuff, and I was happy to do it. So if people take just a little bit of value away from it, if it's even as simple as just, checking where they're at in terms of their bump and droop travel, fantastic.
Yeah. We've had conversations, not just you and I, but me with other people, but you have to put in the work. You have to educate yourself. Just going to the track won't necessarily always net you the results you want, right? And when you hit a wall, these are the times to educate, not hit a wall literally, but figuratively. let me fix that. These are one of the times you want to educate yourself and explore your vehicle in a way that you're going to have to educate yourself on and learn and see, did you do it right? Right is in quotation marks. I'm air quoting myself, yeah. And just explore what's going on. And so you're a more educated track driver, racer, time trial, or time attack, whatever. I think that's the most important thing. So,
yeah, exactly. And I would certainly not encourage anyone to pull their car apart and start checking this stuff the day before a race event. But if you're mid, if you're in the off season, or you're in the process of saving up for new tires or whatever, this is something you can do to just check where your car's at. When your car was completely stock, these things, the bump and the droop travel and the bump stop engagement points, were all checked and established and known by the OE. And then when you've modified it by installing coilovers and then further modified it by potentially changing control arms or doing other bits and pieces, you're now pretty far away from that stock setup. So you can't assume that what you've done now has any relation to what it once was. So certainly worthwhile, touching base and checking those things.
Absolutely. And if you're like me, who's got a perfectly functional car, driving almost right where he wants it to be, but you're looking to do something dumb like spend a lot of money on new dampers over next off season, you should definitely go through all of this, because look at all the ways to set things up and make sure that when you buy the new ones, they're set up correctly. So, Grant, thanks again. I appreciate it, sir.
No problem. Thank you. Cheers.
Until next time, keep working on yourself, keep working on the car, and let's get faster.